So what was the last topic we have seen yesterday? Directional analysis of the motional EMF, right? No. So let me continue with the topic. Listen here. So we have got the direction of the current also in this case. No, if I try to move this with velocity v, and this is my magnetic field which is inside the board, and the current direction is towards up. Yes sir, no, the flow of current is towards up. So this is current direction, and this is my electron direction. No, in the opposite direction of the current, electron will flow. Now if I want to represent this diagram in terms of circuit, so this is my circuit, so negative to positive, so this is my circuit. You can take that circuit. So if the current flows in the downward direction, which means electron will flow in the upward direction, then if current flows downward and electron will flow upward, so in that case the diagram will be looking like this. The batteries are interchanged here. No, completed? No sir. Okay. Write down applications. So in application, let me take 3 cases. So there is a conductor, and now the current is flowing in this direction. So I will take that current as uniform current. What is the meaning of uniform current? Constant flow, right? Now if the current is constantly flowing in the rightward, obviously when the current flows, the magnetic field will be created, and it is uniform current, then uniform magnetic field will be created. So will there be any change in flux here? Any change in flux? Then what about the induced EMF? Will be equals to, if there is no flux change, what will be the induced EMF? 0. Then induced current also will be 0. This is the first case. Take down. When the current is uniform, induced EMF and induced current will be 0, because there is no change in flux. case 2. So there is a conductor and current is flowing from left to right, and here I am taking, it is increasing in current, like current is increasing, which means like with respect to time current is keep on changing. If current changes, what about the magnetic field? If magnetic field changes, obviously the flux also will be created. So if there is change in flux, obviously induced EMF will not be equals to 0 and induced current also will not be equals to 0. So what is the direction of the induced magnetic field created for this current? Outward or inward? Use the right hand thumb rule. This is my current direction. I am curling my fingers in the outward direction. Then this is my current, like a magnetic field, no? Outward, no? Inward it is cross mark, outward it is point. So I am going in this direction, which means the thumb denotes the current direction and the palm denotes the magnetic field direction. So I am curling my palm towards me, so which means magnetic field will be outward. Okay. Now the question is, I need to reduce the current. Okay, I need to reduce the current. So to reduce the current, I need to oppose the magnetic field, right? So in which direction I should oppose? Opposite direction, which means this is my opposite direction, no? And this is called as induced magnetic field. Induced magnetic field. Listen carefully. I have taken a case. The first case is uniform current, which means there is no change in magnetic field. Since there is no change in magnetic field, flux is also will be 0. Since flux is 0, induced EMF is 0. So since EMF is 0, current also will be 0. The first case completed. Second case, I am taking the current is increasing with respect to time. Since current is increasing, obviously magnetic field will be also increased. So magnetic field increases means change in flux will be obviously there. If change in flux is there, so in which direction the magnetic field is coming? Outward direction. So I have taken induced EMF and induced current is not equals to 0, which means the current and EMF is increasing with respect to the current which is flowing here. Right now this current is different and this current is different. This is induced current and this current is a normal current. Now I need to oppose the induced current. So to oppose the induced current, I need to oppose the magnetic field which is created by this current. Right now, so to oppose that magnetic field, I am using the other magnetic field which is inward. That magnetic field is called as induced magnetic field. So what is the direction? That is inward direction. Okay, this is the second case. Take down. So any doubt in the two cases? Once you have completed, we can go for the third case. Completed? Not completed. Done? Okay, I'll take the case. So there is a conductor and current is flowing from left to right, but I am taking the current as decreasing. Okay, current is decreasing. Now will there be any change in magnetic field? Yes or no? Obviously change in magnetic field will be there because current is decreasing. No, either it is increasing or decreasing, magnetic field also keep on varying. Since magnetic field is varying, obviously flux also changes. So since flux is changing, obviously induced EMF will be created, induced current also will be created. So induced EMF is not equals to 0, as well as induced current is also not equals to 0. Now what is the direction of the magnetic field? Same outward direction only. Current is going in this direction only, no? And magnetic field will be outward only, no? But the thing is, current is keep on decreasing. I need to increase the current now. If I need to increase the current, what is the direction of the magnetic field I need to take? If I want to pull the door towards me, I am not able to pull towards me. What is the direction I need to use? Outward direction. If I keep outward, no, again I can't, it will go out. Inward only, no? Yes or no? Okay, for example, there is no one in the room. Okay, if I try to open the room, I need to push inside, right? No? With one person energy, it can be done. Okay, now if I ask 2 or 3 person to come and help me, in which direction they will help? In the same direction of me or in the opposite direction of me? How opposite? Same direction, no? Here also, like current is decreasing. If I want to increase the current, I need to increase in the same direction only, no? So induced magnetic field also will be in the same direction. Okay? Induced magnetic field. When the current is increasing, induced magnetic field will be inward. When current is decreasing, induced magnetic field will be outward. Okay, so now you have taken this 2 example, like I have taken the 2 conductors in a circular thing. Now let me consider as a rod for the both cases. Okay, for the first case, induced magnetic field is inward, no? So which means I need to keep my palm in inward direction. So what is the direction of the current? Upward. So this is my direction of the current. When I talk about the circular, this is my direction. Getting? Similarly, if I want to talk about this one, will be in the opposite direction, no? Yes or no? So for this it is inward, which means it is going upward, like it is anti-clockwise, right? I mean it is clockwise, and this one will be anti-clockwise. Okay? you can take the direction of the induced magnetic field current. Give the notes. So in Faraday's law, we have taken the example of the conductor, no, the circular part, like the circular ring. In the uniform magnetic field, I have taken the circular ring. If I try to pull it either left side or right side, okay, in the uniform magnetic field, the induced current will be, or induced EMF will be 0, yes or no? But if I try to, like, I am pulling the object like this, which means it cuts the magnetic field, but whatever it is cutting, it has been included this side because it is uniform, no? So if I take a circular ring, if I try to pull right side, no, what happens? It will cut the magnetic field, but whatever it is cutting this side, it will be included this side, no, because everything is uniform, yes or no? If one is neglecting here, plus one will be added here, no? So which means I can say in this case induced EMF or induced magnetic field will be, induced current will be 0, but if I try to rotate like this, it is changing. That's the case we have talked now. So from this point we can understand that for a closed loop, induced EMF is 0. Okay, write the point. For a closed loop, induced EMF is 0. For a closed loop, induced EMF is 0. So if induced EMF is 0, induced current also will be 0. So motional EMF has been completed. Now the rotational EMF. Rotational EMF. Listen here. So point A has been fixed in the space, okay, and magnetic field is created inward. If I try to rotate like this, obviously the magnetic field will be cut. Right now, if the change in magnetic field will be there, flux will be created. Since flux is created, induced EMF and current will be also created. Okay, take the diagram, I will tell the points. Done. So in motional EMF we are trying to take in the horizontal direction, which means only one direction we are talking, right? So there we have talked velocity. Here we are talking about the rotational. Since we are talking about the rotational, it is angular velocity. When we rotate with an angular velocity, write down, when we rotate with angular velocity omega, when we rotate with angular velocity omega, the object cuts the magnetic field, the object cuts the magnetic field, next point, since change in magnetic field is there, flux has been created. What flux it is? Magnetic flux. Next point. So induced EMF and current also created. And the formula for the induced EMF is E is equals to half BL square omega, and the fixed point is always called as positive pole. And the free end, next point is, and the free end is called as negative pole. Fixed end is positive pole, free end is negative pole. So now the case is, I have taken the magnetic field, now the object is the same rod, but the fixed position I have taken at the center point. Let me call that center point as O, and this is A and this is B. Okay. So what was the previous point? Fixed point is always called as positive and the free end is called as negative. This is my positive and this is my negative. A and B are negative, O is positive. What is the formula we have talked? E is equals to half BL square omega. Okay. Now if I talk about the induced EMF of OA, which is nothing but only these 2 points, what is the length of the total rod? It is L. I have taken exactly midpoint, which means this is L by 2. Right now, if it is L by 2, it is half B L by 2 whole square omega. Right. Similarly, EOB will be also equals to 1 by 2 B L by 2 whole square omega. Okay. Now if I talk the total induced EMF, which is nothing but EAB, it is 0. It is 0 because both are having same potential. The potential difference will be 0. Okay, both are having same potential and the potential difference will be 0. If they are talking about the separate cases, what is the case of OA and what is the case of OB, then I can talk about this formula. If they are talking about this whole case, when I have fixed the point in the middle, then the induced EMF will be equals to 0 because the reason is same potential difference. OA also having a potential for example 5, in the sense this also will be having 5. So change in potential will be 5 minus 5, 0. Okay, take down. Right on the next topic. Energy dissipated, energy dissipated, energy dissipated. So what is the power formula in terms of voltage and resistance we have seen in the current electricity? V square by R. So power is equals to V square by R. What is V? Voltage, right? Now here we are talking about the EMF. Which EMF we are talking? Induced EMF. What is the motional induced EMF formula? Yep, E is equals to BLV sin theta, right? Now so I can take E is equals to BLV, okay, B into L into V for the maximum I have taken, okay. Sin 90 is 1. So can I substitute the value? P is equals to E square by R also I can write now. EMF by like EMF square by resistance. Voltage and EMF are same only, no? Voltage and EMF. So I am talking about the induced EMF here. So which means BLV by R, that is BLV whole square by R. So what is V here? Velocity, length, magnetic field. So it is B square L square V square by R. This is my energy dissipated formula for the motional EMF. Take down. The next topic is inductance. Right on the first point, it is the nature of the circuit, it is the nature of the circuit to oppose the current, to oppose the current. So SI unit is Henry, SI unit is Henry, denoted by the letter H, and the symbol is looking like this. This is the symbol of the inductance. So oppose the nature of the current. Okay. Similarly, we have talked about the opposing nature of the current in current electricity, resistance, right? No. Okay. Suppose if I take a circuit, okay, I have taken the circuit. Initially, at time t is equals to 0, I also will be equals to 0, right? No, when I start connected, like switched on, no, the circuit, the current starts flowing to the maximum level, to the maximum level. Whatever the battery is there, which is fully charged, if I try to switch on the like switch, no, like if I on the switch, what happens? It will start flowing immediately to the maximum level. Now what happens when it comes to this point? That maximum level becomes minimum because of the inductance, which is opposing in nature, right? No, take the circuit. It is battery. One is big and one is small. Write down. At t is equals to 0, at t is equals to 0, I also will be equals to 0. At t is equals to 0, I also will be equals to 0. The next point, when we switch on the circuit, when we switch on the circuit, I goes to maximum, I goes to maximum, which means the flux also goes to maximum, right? Because it is a ring, no? It is a ring. So obviously the magnetic flux will be created. If I is there, magnetic flux also will be created. But because it is increasing, no, sudden increases means magnetic field will be created. Due to that, flux also will be created. Okay. So if it is created means obviously induced current also will be created, no? The next point, again it will go from maximum to minimum. Again it will go from maximum to minimum. Again it will go from maximum to minimum. Because of the inductance. Because of the inductance. Okay, listen here, listen. So I have switched on the circuit, which means the current suddenly increases. If sudden increases is there means magnetic field also will be there, like change in magnetic field, flux also created, which means induced EMF and induced current also will be created. Now I am coming this to this point exactly. When I come to this point, again sudden decrease will be there because of the inductance. Okay. If sudden decrease is there, again flux also will be changed and EMF will be created again. That EMF is called back EMF. That EMF is called back EMF. Due to this battery, sudden increase was there. That increase was I have taken as induced EMF. Okay. First case, sudden increase in current, which means magnetic field also increases. Yes, no, magnetic field increases means flux will be created. Due to that, induced EMF is there. Induced EMF is there. When I come to exactly this point, this is inductance. Now what is the meaning of inductance? It will try to oppose the current, right? No, so induced current also will be created there, but that induced current has been opposing there. Yes or no? Induced current has been opposed here. So if induced current has been opposed, like magnetic field will be decreased. Yes or no? Magnetic field will be decreased. So flux also will be changes. So which means that EMF is called as back EMF. That EMF is called as back EMF. Okay, write down. Due to sudden decrease, the field will be changed, and again induced EMF will be created, that EMF is called as back EMF. That EMF is called as back EMF. Okay, so induced current ఎందువల్ల ఫామ్ అవుతున్నది, లైక్ డ్యూ టు ది నార్మల్ కరెంట్. బట్ బ్యాక్ ఈఎంఎఫ్ ఎందువల్ల ఫామ్ అవుతున్నది, ఇండ్యూస్డ్ ఈఎంఎఫ్ వల్ల ఫామ్ అవుతున్నది. ఓకే, అండర్స్టాండ్ ది పాయింట్. నౌ రైట్ ది సెకండ్ పాయింట్, ద నెక్స్ట్ పాయింట్. induced current developed in such a way that it opposes the main current. Induced EMF is developed in such a way that it opposes the main current. So can I write flux is directly proportional to current? If current increases, flux also increases or decreases. Yes or no? Current increases or decreases, flux also increases or decreases. To remove the proportionality, we are adding a constant called L. Okay, that L is called self inductance. Okay, self inductance. Now we are going into the topic self inductance. Okay, we are already in the topic of self inductance only. Now I have introduced the term L, that is self inductance. If n number of turns are there, listen, if n number of turns are there, n into phi is equals to L into I, then the formula will be L is equals to n phi by I. N is the number of turns. Done? Okay. What was the relation between the EMF and the flux? E is equals to minus d phi by dt. Which law? Lenz's law. Minus d phi by dt, no? E is equals to minus d phi by dt. What is phi here? L into I. So minus d by dt of L into I. Right? So if anything is changing with respect to that, I can take the components. So if current is I, then minus I into dl by dt. This is my induced EMF. If current is varying, then what happens? L into di by dt. If current is varying, no? If current varies, L will be constant, no? Yes or no? Done? Completed? Any doubt in the self inductance? Self inductance topic is completed. Now we will go for the mutual inductance. Okay, mutual inductance. Self inductance means due to the self circuit. Okay, due to the own circuit, the EMF is created. Now the mutual inductance, write on the topic. Mutual inductance. So which is denoted by the letter M. Now I will take two circuits here. Listen. So there is a conductor I have taken which is connected with a battery. So if battery is connected, obviously the current will be flowing, no? Yes or no? If current is flowing, like I have switched on the switch immediately, which means the current flows to the maximum. When it flows to the maximum, obviously the field will be created or not? Magnetic field. So the magnetic field has been created. So due to the magnetic field has been created, like it will be changes, no? Yes or no? It is changing, then like the current is changing, sudden increase will be there, again the flow will be normal. So in that case, sudden magnetic field will be created and it will flow. So when it is flowing, no, like it will be flowing in this also. I am keeping adjacent side. Okay, I am keeping the adjacent side. So obviously the magnetic field will be flowing in this also. If a magnetic field will be flowing in this, the change in magnetic field creates means obviously flux will be created. So due to flux created, induced EMF also created. So I am creating my own EMF in this circuit. Am I creating any own EMF in this circuit? In the first one, I have created my own EMF. But in this case, I am creating the EMF adjacent circuit, by the adjacent circuit. I am getting the help of the adjacent circuit and creating the EMF, right? So that EMF is called as, like due to that I am calling that as mutual inductance. Mutually I am getting that from the adjacent circuit. Okay. Then flux will be directly proportional to which current? Primary current or secondary current? Primary circuit, no? Whatever the current flowing in the primary circuit, due to that only flux has been created. So that then phi will be equals to M into IP. So this I is nothing but primary current. So the primary circuit, because of the primary circuit, I am getting the induced EMF in the secondary circuit. So this is mutual inductance will call, and I need to consider that current as the primary current. Okay, take down. So what flux is this? Secondary flux or primary flux? Secondary flux. So secondary flux is created by the primary current. Okay, secondary flux is created by the primary current, that is called as mutual inductance. So what is the formula for the EMF? E is equals to minus d phi by dt. So what is phi here? M into I. So minus d by dt of M into primary current. So mutual inductance I can take out. So minus M di by dt. This is my EMF. ఏం చేస్తున్నారు మేడం? బ్లెస్సింగ్ చేస్తున్నది ఏంటి? Two coaxial solenoid. Two coaxial solenoid. Coaxial solenoid. Solenoid means like we have learned the solenoid, no? Like n number of turns will be created. Okay? Two coaxial in the sense so it has been connected in the opposite direction, which means I can connect with this mutual inductance. If any flux is created by the first solenoid, it has been transferred to the second one and I can get the EMF, right? No, take the diagram, I will tell the formula. This one, so this is N1 and this is N2, N1 turn and N2 turn. So first solenoid and second solenoid. M is equals to mu naught N1 N2 A M is equals to mu naught M1 M2 A divided by L. Mu naught M1 M2. So like due to M1 how many turns if it is there, I can take that as turns, like number of turns, and M2 the number of turns I will take. Okay, so in M1 I can take N1 number of turns, and from M2 I can take N2 number of turns. And you know the relation between the mu naught and mu r, no? Relative permeability, right? No, write down the next topic. Energy stored in inductor. Energy stored in inductor. Energy stored in inductor. U is equals to 1 by 2 Li square. 1 by 2 Li square. 1 by 2 Li square. Next topic, series and parallel combination of the inductance. Series and parallel combination of the inductance. Series and parallel combination. Suppose if I take the series combination L1 L2, then L will be equals to L1 plus L2 for the series combination. The L effective will be equals to L1 plus L2 for the series combination. So under this you can take a point, same current. If I talk about the parallel combination L1 L2, so 1 by L effective will be equals to 1 by L1 plus 1 by L2. So here same potential. Completed? Relation between completed. Write down relation between self inductance and the mutual inductance. Relation between self inductance and the mutual inductance. Self inductance and the mutual inductance. So when I talk about the inductance I have connected here, no, obviously one will be connected with the other one, right now. So obviously the flux also will be keep on changing with respect to the other one, right. So I can write the relation here, m is equals to root over L1 L2. M is equals to root over L1 L2. M is equals to root over L1 L2. This is my relation. Write down the application again. First one series combination. First one series combination. Series combination. First one is series combination. So series combination in the sense like I will take L1, L2. What is the current flowing? Same current or different current? Same current. What is the potential? V1, V2. Okay. Then L effective will be equals to, write down, L effective will be is equals to L1, L2 plus 2m. L1, L2 plus 2m. It is the relation in terms of self inductance and the mutual inductance. Okay. Completed. So next is parallel combination. So what happens here means L effective will be equals to L1 plus L2 minus 2m minus 2m. The same thing I have bent in the other form. Okay, I have taken the same circuit, but I have bent in the other form, which means in this circuit the current is flowing in this direction I, in this circuit the current is flowing in the opposite direction, right? No, for the first one in the right, for the second one it is left. That's why we have taken the minus symbol. So the minus symbol denotes that current are in the opposite direction. Completed. So take a look into the notes whatever we have seen now, and we'll go first the cases of the inductance. Okay, listen. So we'll talk about the three cases. So let me take the inductance. So where the current is flowing here, it is I. So let me take it's a constant current. The first case is constant current. Second case is current is increasing. Let me take current is increasing, and the third case is current is decreasing. So what is the formula? E is equals to minus L into di by dt. Yes, no? Since current is constant, if I differentiate the constant, 0, no? So EMF will be 0. Getting the point? Second point, current is increasing, which means positive, right? So I is positive, current is increasing. So E will be equals to minus L into di by dt. This is my formula. But when I go for the third one, current is decreasing, which is negative. Current is negative. Okay. So E is equals to minus L into minus di by dt, which means L di by dt. So try to use the formula properly. When the current is increasing, I will use the formula minus minus L into di by dt. If current is decreasing, L into di by dt. The symbol changes, the sign changes here. Okay. These are the three cases. So with this, I will complete this one, and we will see in the next class.